So welcome everyone. This is a Stride-sponsored webinar that focuses on big data and detecting and characterizing demand and incident-induced congestion. I'm pleased to be here as one of the presenters. My name is George List, and I'm a faculty member at North Carolina State University. I'm joined by Mohammed Hadi, who is a faculty member at Florida International University, and by Schumann Gwynn, who is a research associate at Georgia Tech. We're going to be sharing responsibility for the webinar today. There is a chat box. There's also a dialogue center where you can enter questions that you'd like to see us address. And at the end, we'll be happy to answer any questions that have arisen as a result of our presentation. The presentation, the webinar, is part of the efforts of the Stride Center. It's a collection of universities that are participant in the Region 4 University Transportation Center. You can see the names of all of the participating universities in this slide. And if you happen to know someone who is a member of the faculty or is a student at one of these universities, or if you would like to get in touch with one of these universities to find out more about the Stride Center, we would certainly encourage you to do that. The team that works on the material being presented today, as I have already mentioned, come from three universities. In addition to myself at NC State, Billy Williams, Ishtiaq Ahmed, and Ahmed Abdallah. At Georgia Tech, in addition to Anshuman, we have Michael Hunter and Nishu Chaudhry. At Florida International University, in addition to Mohammed, we have Atika Jabin and Hector Mehta. And very happily, we've been working together extensively and closely since the beginning of this project. And so anything that you're seeing today is a result of an intense dialogue that's occurred between all of these individuals on about a weekly basis related to the topic. So to give you a sort of framework from which to see the rest of the presentation, congestion onset detection, it's nominally easy from live video streams, but it's difficult to automate that procedure, as you will see from the rest of the presentation. Our early detection of congestion onset and its cause is helpful. It's critical for deploying operational measures and or alerting first responders in case it happens to be an incident that's caused the congestion. There are prediction algorithms, and that's been our focus, to allow traffic management agents to take preemptive actions like the ones I just mentioned in order to mitigate or to ameliorate the impacts of the events. And the data streams that we're working from are things like travel time statistics from probes, information we can collect from basic safety messages that come from connected vehicles, and then also system detector data that might come from video cameras or from loops in the pavement that it would indicate traffic flow disruption and give us a hint as to what the cause might be. The goal in the project has been to identify the onset of demand-induced congestion, as well as the occurrence of disruptive incidents, incident-induced congestion. In what we're talking about today, the scope has been freeways. We do have an objective of focusing on arterials as well, but we have yet to really make a lot of headway in that domain. The presentation in our work has been sort of focused on three case studies. Those of us at NC State have focused on a case study framed around Sacramento, specifically Interstate 5, using probe data that was obtained from Bluetooth sensors, augmented with weather and incident information that comes from their incident management system. In the case of Georgia Tech, it's been Interstate 85 in Atlanta, where they're collecting speed data and other kinds of information from a video detection system. And then in the case of the Florida National University work, it's been Florida 618, or the Turnpike Authority facility in Tampa, working from the input stream of basic safety messages that were coming from connected vehicles. So I'm going to talk briefly about the Sacramento case study. Let me get started on that. The data that we happen to have came from a collection of Bluetooth observation stations. There were 4 of them. We are using the outside 2 from January through March of 2011. We got probe data between the endpoints, but we can also observe the headway between successive probes. And we did have to do some data cleaning in order to be able to separate the signal from the noise that was part of that data source. We also got supplementary data from PEMS, like travel times as observed by the system detectors, as well as incidents that have occurred within this region. And we then did some manual adjustments to the designation of when the incident started and completed by manually doing adjustments on the basis of observations of the travel rates and so forth on the facility. This is a brief screen picture of what the raw probe data look like. You can clearly see the bulk of the observations are around a minute per mile, except when there are incidents like this big event that took place here in February and other either peak load conditions that existed like these 3, or in fact, incidents that happened to have occurred in addition to those peak load conditions. And the data that are here, much above the 1 minute per mile, you might term as being snow. It's also noise. It's data observations that were picked up by the Bluetooth sensors. They, just for purpose of illustration, might have been a vehicle that got on at one entrance ramp, traveled on the freeway for a while, got back off, got onto the arterial network, did some things, and then got back onto the freeway network, and were observed somewhat later at the second observation location. And so it's a legitimate observation of the travel time between the 2 sensors for a vehicle. But in terms of characterizing the travel times for the freeway corridor, not all that useful information needs to be filtered out. That's what we did. And if you look at the blue trace that's here, that's the result of the filtering that we did. And although it looks snowy again, what you're actually seeing is the green data, and that is information about the headways that exist between the successive probes. And so you can easily spot the overnight conditions when the headways get long, and then the headways are quite short, where there's a high density of the green data points during the middle of the day, starting from just before the AM peak until after the PM peak. If you look at this particular plot, you're seeing that expanded so that you can see individual data points. Each one of the dots is an individual probe, and reported for that probe is the travel rate that was observed between the 2 Bluetooth observation locations. And then the green line is indicating what was the headway between that observation and the one that preceded it. And you can see again that in the overnight hours, why the headways become fairly large, in fact, larger than is depicted on this diagram. But during the middle of the day and during the peak hours, why the headway between the observations, Bluetooth observations, gets quite short. Get down to about a quarter of a minute, 15 seconds or thereabouts. The method that we employed to investigate, and if I happen to use DIC and IIC as acronyms, they stand for Demand-Induced Congestion and Incident-Induced Congestion. The methodology we used was to process the observations in chronological order and then create sets of 30 observations, could have been 50. We experimented with numbers from 10 to 50. What is being reported here today is predicated on observation sets of 30. And our primary intent was to look at the 5th and 95th, or if you will, the fringe percentiles of the distributions of the travel rates for those sets of 30 observations, and then to track trends in those fringe percentiles and observe not only their individual values, but the differences in their values, and use that information to identify the occurrence of demand-induced congestion and incident-induced congestion by observing those trends. The picture that's at right shows 4 pieces of information. The purple line is the 5th percentile travel. No, the orange line is the 5th percentile travel rate. The purple line, that's not true. The purple line is the 5th percentile travel rate. I apologize for confusing you. The purple line is the 5th percentile travel rate. The red line is the 95th percentile travel rate. This orange line is the difference between them, the spread in travel rate between the 5th and the 95th percentile values. And then the blue line is an indicator, an integer indicator that we created or an indicator with a collection of values that we created to identify the conditions that were underway. Like if it's a 0, that means there's nothing extraordinary that's taking place. If that happens to be a value that's in this range, then it's indicating that there's a weather event that's underway of some kind. And if there are values up in the range of 1 to 1.5, why there are peak load conditions that are occurring, or incidents that are occurring, or a combination, in fact, of those 2 events. And we use that information as the way to check to see whether or not demand-induced congestion or incident-induced congestion had occurred. The ambient condition flag is indicated down here: 0 for nothing, 0.1 for mist, 0.2 for rain, 3.3 for wind, 0.4 for fog. And if there was a incident that occurred in conjunction with that, then a leading 1 was included. And if it was during the peak hours, why an additional flag was set. Key observations that we derived from examining the data. The first one is that the 5th percentile travel rate seems to increase, and it increases gradually as the traffic conditions trended towards demand-induced congestion. We perceived that this might be attributable to the fact that the faster moving vehicles are having to slow down because of the increased congestion. They're not able to make lane changing maneuvers or to thread their way through the traffic and achieve the higher speeds or the lower travel rates that they would like to see. We also observed that the spread between the 5th and 95th percentile travel rates seemed to increase abruptly when an incident-induced congestion event occurred. And you can postulate why that might be, but our sense was that this could occur because some of the vehicles are delayed. They come to a stop or they slow down because of the occurrence of the incident, while others are able to maintain a more reasonable speed. If you think about it being in the right-hand lane or the left-hand lane, why the effect on the traffic not only will be different, but there will be vehicles that are slowed down. And so the difference between the 5th and 95th percentile rate seems, from the data, appears that spread increases when there are incidents. We did analyses more driven by human analysis than machine learning. In this particular instance, looking for breakpoints or indicators that would be indicative of demand and incident-induced congestion. Here's what we found. Through sensitivity analyses, seem to work very, very well. In the case of the demand-induced congestion, if the 5th percentile travel rate rose above 0.9 minutes per mile, then there seemed to be an indication that demand-induced congestion had occurred. And we set an incident-induced congestion flag of 2.25. The number is arbitrary. It's just so that it can be seen in the plots. Insofar as incident-induced congestion is concerned, we found that the spread between the 5th and the 95th percentiles, if that rose to be more than 0.4 minutes per mile, then there was likely to have been an incident that occurred. And we set what we called an incident flag and set the value to be 2.0. Again, an arbitrary number, but it is helpful from analyzing the plots to see where that flag has been set. And then if we detected both of these events, that demand-induced congestion and incident-induced congestion had occurred, we set an additional flag to be 2.5 on the basis of the fact that not only was the 5th percentile travel rate above 0.9 minutes per mile, but the spread between the 5th and the 95th percentiles had reached a value, or it obtained a value that was more than 0.4 minutes per mile. We needed to test to see whether this diagnostic tool would work, of course, intended for use in real time. And we did that on the basis of using the team and some colleagues of ours to do a visual assessment of the trends in the travel rates and determine whether or not, in our collective opinion, demand-induced congestion had occurred or an incident had occurred by watching those travel rate traces. And we looked at 4 different classifications or 4 different assessments, things that you would expect: a correct positive, a false positive, a false negative, and a misclassification. Let me describe those briefly. The correct positive, the tool or the data analysis suggested that the onset of demand-induced congestion had occurred, and or the occurrence of incident-induced congestion, and the raw data suggested that in fact that was correct. If there was a false positive, then the tool indicated that either demand-induced congestion or incident-induced congestion had occurred, and the raw data suggested that an event had not occurred. And then the false negative is that the diagnostic tool indicated that nothing had occurred, but in fact the data tended to suggest to the people viewing the data streams that in fact something actually had occurred. And then misclassification would be an instance in which the tool diagnosed the situation as being either demand-induced congestion or incident-induced congestion, or the combination of the two, and yet the people that were reviewing the data stream reached a conclusion that in fact that was not the case, or it had been misclassified. So here's the table that presents the results of that analysis. And let me focus on the fact we've got 2 directions, southbound and northbound. And then we separated the data into daytime and nighttime hours, in part because of the headways that we observed between the probes. And the daytime was defined to be between 6 a.m. and 10 p.m. The nighttime was the rest of the day. And here are the number of records that we have for each one of those instances. And here are the various kinds of congestion, whether it's incident-induced or demand-induced or the combination of the two. Here are the number of times that the tool spotted the fact that that congestion occurred. Here are the instances in which it was deemed to be a false positive. That is, that the tool perceived that it had arose when it didn't. Now, this is the number of times when the tool correctly identified that it occurred, and the reviewers concurred with that. And then this is the number of times and the percentage of misclassifications. And if you look at the table, you quickly identify that it has some challenges at night. And our assessment of that is that the sparseness of the probe observations is the thing that is creating that challenge, because the time interval between the first and the last probe observation for 30 observations is quite long at night. And so the tool is maybe perceiving that something had happened when in fact it had not. In the case of the daytime, here is the number of correct positives insofar as incident-induced congestion, and the correct positives in terms of demand-induced congestion. So in these instances, not only did the tool diagnose that there had been demand-induced or incident-induced congestion, or for that matter, the combination of the two, and that the people who reviewed the time traces concurred that that was in fact the case. Here are the instances in which the The tool said that there was an event that had taken place, but in fact, the reviewers perceived that there wasn't. And this is the number that were misclassified. And you can see that during the daytime, whether we're looking at northbound or southbound, why the performance is significantly better. You might notice that down here for the incidents that it's not as though it didn't detect the incidents, but rather that it might have had a bit of difficulty identifying and correctly classifying the incident as being an incident as opposed to demand-induced congestion. I also want to draw your attention to the fact that the false negative column is in fact blank. There were not any instances in which the detection algorithm perceived that nothing had happened when in fact something had. So the tool in its current state is quite able to identify that something has occurred, either an incident-induced congestion or demand-induced congestion. Although, as you can see from this misclassification column, it has a bit of a challenge in terms of putting it into what the reviewers would perceive to be the correct category. So, discussion in the context of what we've done, a high percentage of false positive demand-induced congestions in the nighttime, and that underscores the need for incorporating the headway information maybe into the diagnostic tool, that we don't have any false negatives, and that the percentage of misclassifications is a bit on the high side, and that is compounded or complicated by the challenges of parsing between demand-induced congestion and incident-induced congestion, and the fact that perhaps a little more enhancement of the tool would be helpful. I'm going to pass the baton to Gwyn, who's going to talk to you about the Atlanta case study.
All right, thanks, George. Let me take over the screen here. All right. So as George explained, means our purpose here is to identify the imminent onset of congestion so that we can take actions ideally to prevent and the onset, or at least minimally to delay the onset of the congestion. Like for reference, the holy grail of traffic operations is usually, especially in the freeway operations case, has been to stabilize and maintain the traffic in the top right zone of the speed flow plot, and to prevent the breakdown of the flow so that it enters the bottom area, the reduced efficiency area. So in the Atlanta case study, we focused purely on the recurrent congestion case. Similar to the NCSU study, our assumption here is that there are some artifacts or anomalies in the data that would provide an early indication that the instability in the flow is increasing to a point where the failure is imminent in the next 5 to 15 minutes. As the question is, why does it matter? Like, we all know that the flow breaks down on most of Atlanta's freeways sometime between 4 and 5:30 p.m. and in most other cities as well. But if you look at the onset of congestion over different days, you will notice that the time of onset of congestion is not exactly the same every day at any given point on the network. Every interchange on the network is potentially a bottleneck, depending on slight variations in the demand. The different bottlenecks can fire up on different days. So we want to get an early warning of which bottleneck is about to fire up today in the next 15 minutes, so that we can try to take precise and targeted corrective actions. So for this one, we went with a machine learning approach. We can, of course, contend that a lot of work has already been done in predicting flows and speeds. And if you predict these two, means you know when the demand exceeds the capacity and the flow will break down. But for most of those predictions or the predictive approaches, we are essentially looking to identify a trend and suppress the noise. Right? Whereas in our approach, we are looking for precursors. So we are leaning more towards subtracting out the predictable portion, the trend that is, and looking at the noise or the apparent noise to see if there are any identifiable patterns that would give us the precursors to the congestion. So in our study, we went with a supervised learning approach. Once we know quite precisely where the breakdowns occur just by looking at the speeds and the flows. So, but our goal here is not to identify when that break occurs, but get an early warning of when that break will occur. So we tag the data points for the last 5 minutes as ones, or those are the points that we want to find as precursors, and the rest are labeled as zeros, that those are not indicative of an incident. Now, this is kind of a shotgun approach, and that this 5-minute interval is somewhat ad hoc, but we have previous literature indicating that there are the instabilities happening in the 6 to 30-minute region leading up to a breakdown, where which could be indicative of an oncoming breakdown. So we started, means this is a shotgun approach, means we labeled all the points as ones, although once we can contend that there might be only one point which is actually a precursor and the rest are normal points. So we started there. We'll come back to the discussion in the results. So and also any data after the flow has broken down as the speeds have gone down, means that's not relevant to us because we know that it has broken down. So there are no precursors leading to a breakdown. Anyway, enough of that. So for our side, in Atlanta, we looked at I-85 inside the 285 perimeter. Right here at the bottom, here's downtown Atlanta, and I-75-85, it splits here. So this top right-hand corner is that's our spaghetti junction, which is it's probably called so because of the structures, but if you look at the operational status, it won't be too far fetched to call it spaghetti. Anyway, so that we looked at this northbound approach of the corridor. So we know that there is a recurrent congestion at this I-285 and 85 interchange here, the spaghetti junction, in the afternoon peak on the reverse commute every day. So we wanted to make sure that the other congestion that's happening at this Claremont Road exit, if you look at this space time plot here where the color indicates the speed, so you'll see that in this particular case, for example, there are two distinct bottlenecks, and there is no impact of the bottleneck from the spaghetti junction on the bottleneck at the Claremont Road. So the queues are not flowing through to this bottleneck, and there is no confusion because of that. So this is the ideal scenario on which we would like to train our data set, because we are sure of when the bottleneck actually fired right here. So we will be looking for anomalies in this region leading up to that firing. Here's some more of examples here. So for example, if you look at the April 18th data here, and so you see that the queue here kind of flowed through in here and got mixed with it, although you can say that this bottleneck actually started off here around like 350 or so. So means although it's a mix, means it's not that big of a problem. On this one, on the bottom one, it's a little harder to be sure, because there seems to be a little bit of a breakdown here, and then it kind of goes away, and then it fires up again as the tail of the queue from the I-285 one. So why am I showing you these? These are quite relevant when we are trying to train the data set. And so, as I mentioned at the top, we are focusing on the recurrent congestion. We are not looking at incident congestion here. In fact, we are trying to remove the incident congestions. We are trying to remove the cases where there is congestion flowing from a different bottleneck. So we want to find out when a bottleneck is firing out at this particular location, so that we can take preventive or corrective measures for targeted or surgical to the surgical precision level for that particular bottleneck. Right? So for this data set, we removed congestion events where the bottleneck was outside the site. We removed the ones where there were incidents specific to this, which were happening within the site. So what do we mean by removing the data? So we removed the data from the period where that incident related congestion occurred. We used the data from the rest of the day. So our data typically started around 7 a.m. because we were had questionable quality of the data during the night. So we didn't really focus on that. It has to be dealt with eventually, but for this to begin with, we went with what we were fairly confident of. So the data starting at 7 o'clock in the morning. So it had, because this is the northbound direction and the congestion happens mostly in the afternoon. So we have a long period of uncongested traffic, and then we chop off the data once the traffic gets into congestion at our site of interest. So we looked at several of the machine learning classifier based algorithms, the basic algorithms. We looked at support vector machines, neural nets, decision trees, random forest, naive Bayes classifier, the usual suspects in this space. And with these, we had about 36 days of training data set. We had 8 days of testing data set. And we created, apart from the basic speed and flow at the site, we created a bunch of derived variables as input to these algorithms, which were, it's based on the neighboring data points. So if you look at the individual detector data at one lane as a point of interest, then you have its neighbors as the other lanes are next to it, and and the upstream station and the downstream station. And also, if you look at it in time, you have nearest neighbors in times the t-1, t-2. So we created a bunch of derived variables looking at the differences between the speeds and flows between the stations with its next lane, with its upstream and downstream lane, and with the difference with a previous time point. So what we see here on the left hand side is this is the original labeling on the test data, where the greens are the labels of zeros, so there is no anomaly, and the yellow ones are, let me go to the next slide where it will be a little better, easier to see. So if you look at this at this right hand side, those are the 5 points in the 5-minute period leading up to the breakdown, which shows the points which we labeled as 1, that these are our points of interest. Now, the bottom plot here shows the points where the algorithm was able to identify these as anomalies or as precursors. So we have the 2 red dots as the true positives, and our algorithm did not identify the previous 3 points as positives. So those are false negatives, because we identified them as true, as positives, but the algorithm identified as negative. And we also got like another point here for further around, like, so around 2:10, so that's about 30 minutes ago, there was a positive. So with our 5-minute window, that is a false positive. If we expand the window, we could think of it as maybe it's a true positive. So there is some amount of interpretation we have to do in terms of what is actually useful information, and not just a theoretical validation of the precision and accuracy numbers. So more examples here, like we had true positives with a couple of false negatives in between, and different patterns of those. So this is a case where our algorithm completely missed it, so it completely failed to identify the onset of the congestion. So we have a bunch of false negatives. So getting into the summary table. So here's on the left of the table, you have the different methods we had. So if you look at a bare accuracy value, means you will see that the decision tree classifier, the random forest classifier, means these have very high accuracy values. But if you look at the false positives, the false negatives numbers, means you'll see that we are getting a lot of positives. So it's again like getting everything that is that could be a precursor, but it's also giving a lot of false alarms. So we don't want that. So I would say that we looked at precision for that reason, and we looked at the ones that gave the best precision, which the support vector machine, the radial kernel, gave the best ones in terms of precision at 0.33, and because the false positives were fairly low. Now, what I want you to think about is what are the false positives with an impact. So if we look at if you go back and look at, say, this example here, so we got a true positive on 2 of the points, and we got these false negatives here. But if we look at that whole event as a single occurrence, then we did find the occurrence. We did find a precursor, right? So I'd say that instead of taking this as 60% false negatives and 20 and 40% true positives, I would contend that this is, from a practical standpoint, this is still a true positive, as a single true positive with 0 false negatives. So if we look at it from that perspective, means this method gave us only 3 false positives and 15 false negatives that had an actual impact on the performance. So the neural network even gave much less false negatives, and it gave a little higher false positives. So we need to think about what the interpretation of this is from the person's perspective. The next steps, once we need to look at this for the transferability across different sites. Once we chose one site, we looked at it, once it worked fairly well, but before we rejoice and celebrate the good performance, we need to look at other sites as well. Also would like to explore some deep learning models. Means the ones we looked at were the basic models, which have very good interpretability, but we want to look at if we can improve the performance better with some of the more advanced models, and also test the performance of this on arterials, because our tests were limited to freeways. With that, I would like to hand it off to Mohammed. Mohammed, you're still muted.
Sorry about that. Okay, thank you, Gwen. So our objective here is in this part of the project, which was conducted with the help of Hector Mata and Atika Jabin, who are PhD students in FIU, is to look at how we can predict these congestion in real-time operation using connected vehicle data. We know that there's a lot of promise with connected vehicle data, with this, collecting data from the vehicle, the basic safety messages. Those will come at 10 times per second, and it will contain safety-related information that is broadcasted to surrounding vehicles, but become captured by the infrastructure and can be used for different applications, both in offline and real time. And the data that we obtained was from the Tampa FIA connected vehicle pilot of the USDOT. And that pilot include arterials, but also include a freeway, the Salmon Expressway. We selected a short segment of that has more congestion than the other segments in the corridor to look at the ability to classify the traffic into pattern and then to predict those patterns. So what we are doing is we are doing two stages. One is unsupervised learning, where we identify the patterns, and then after that we use those clusters or patterns in classifiers to be implemented in real-time operation, as we're going to talk about. So as I mentioned, the case study is the Salmon Expressway, and what we used there is in performance measures that are normally not used in real-time operation, but we could use these based on, or we can estimate them based on connected vehicle data for shorter segment, maybe every 300 feet, rather than the half-mile segment that normally used to predict the performance in real-time operation in traffic management centers. So we used acceleration, deceleration, speed, standard deviation of speed between the data points that comes from each 300 feet, standard deviation of individual vehicles, and because we differentiate between points in this case, between points that come from individual vehicles versus point that comes from different vehicles. So the standard deviation of individual vehicles and the standard deviation between individual vehicles. We also include the jerk as one of the parameters that we investigated. So as I mentioned, our approach was to cluster the traffic into different traffic patterns using the data on those 300 feet using these parameters. And what we found out that we were actually very successful in identifying the different patterns and making sense of those patterns. So we identified 6 patterns or clusters. Cluster 1, 2, 3 are higher speed clusters, but cluster 2 has high standard deviation between points, and cluster 3 has a higher deceleration rate, and maybe that can indicate that cluster 2 and 3, although they have high speed, they may be in the transition to congestion, because one of them has high standard deviation between vehicle and one of them has high deceleration, indicating that maybe there is some traffic coming from the downstream and the vehicle decelerating to it. The cluster 4 is also high standard deviation between vehicle and high deceleration. So that also possibly an indication of transition cluster 5 and 6, both of them are already in congestions, but cluster 6 has higher standard deviation between points, possibly indicating stop and go, heavier stop and go operation, and also maybe a mix of traffic between different vehicles. So in that case, then it looks like just by looking at those clusters, that the cluster 2 and 3 and 4 are potentially the one that indicates congestion coming. They are still in relatively higher speed, but they are possibly indicating congestion coming. And when we draw the time series, we confirm that. So in this case, this is a good example because it shows that we started with the cluster 3, which at cluster 3, as we said, is still high speed, but vehicles start decelerating, indicating there is a congestion downstream. And then after that, the speed started dropping. We still have high standard deviation between point and still have high deceleration rate. So those can indicate that in the next short-term future, we will have a drop in speed. Based on that, then what we did is we used those clusters as input to a prediction model to predict the congestion to be applied in real-time operation. And again, in this case, we use 3 different prediction model, the classification decision tree. We also use a fuzzy rule based system that take the decision tree results and fuzzify it. And then we also use adaptive neural fuzzy inference system that uses neural network back propagation to determine the membership of the fuzzy sets. And we, as Gwen was describing, we examine these different parameters like accuracy, sensitivity, specificity, precision, to see which one of the 3 methods produce better results. And when we look at the results here, we can see that the ANFIS, which is the adaptive neural fuzzy inference system, show higher accuracy, higher precision, and so on, specificity, sensitivity. So, overall, that seems to work with a good level of accuracy and precision, which is a great thing. Again, what we did is we have a training set and the testing set. So this results is for the testing sets that we did. And again, when we isolate also the prediction between situation where there is a breakdown and we are predicting it, and situation where there is no breakdown and also we predict it. So that we wanted to do that because a lot of situations does not have they don't have breakdown, so we did not want to dilute the results by having those no breakdown condition all the time and have high percentage of them. And so here the breakdown one is only when the congestion in the near future, next few minutes, get into congestion. So that's a better indicator in that case. In summary, the study successfully demonstrated the utilization of performance measure derived based on connected vehicle data. Connected vehicle data allows estimating additional measures to quantify performance. Clustering analysis was able to identify 6 different patterns, and was also provide a good input to the prediction. So it's a good way to first do clustering and then do the prediction. And we found that the most important features in traffic state categorization are the speed, acceleration, deceleration, standard deviation of speed between vehicles, and standard deviation of speed between data points. the adaptive neurofuzzy inference system model utilizing the backpropagation optimization method achieved the best performance among the evaluated predictive models. I think this is my last slide. So let me stop share, and now, George, it's all yours.
You're muted.
To draw some conclusions across all three of the case studies, they did look at different case study environments and different data sources and different analysis techniques. I think that's been part of the richness of the overall project and the collaboration to sort of experiment with different tools and techniques that all have the same nominal intent. To identify and anticipate both demand and incident-induced congestion. As we've said a couple of times, the objective here, or the purpose, is to alert traffic management personnel and incident responders as soon as possible in the context of these events, driven by safety and productivity. In the future, why we do hope to look at this in the context of other environments and capitalize on data that we all perceive are coming from probes in the future, as well as system sensors, so that we can understand the trends that exist in the operating conditions. We are interested in applying these ideas and techniques to the arterial environment, and that's sort of the focus of our current and future efforts. We want to see whether the techniques work in that environment and or develop new tools that are applicable in the context of arterial settings. And in the sense of looking at arterial applications, we want to be thinking about fusing the probe data, whatever it happens to be, with data that come from detector inputs and signal actions, because they are very much a part of the arterial environment. That's the end of our presentations for today. We would be happy to answer questions. You can enter them in the chat box. You can also put them in the Q&A box. I've answered some of those as the webinar has been underway. We'll be happy to answer more. And then please do complete the survey. It's very brief at the end of the webinar by clicking the link that's provided in the chat box. There are some upcoming webinars. There's one on micromobility in the context of urban traffic congestion on the 20th of April. There's one that has to do with equity, diversity, and inclusion as a leadership webinar on the May 9th. And then there's an interesting webinar that talks about what drivers really think about autonomous vehicles on May the 18th. You might have seen the recent news clip about a policeman trying to talk to an autonomous vehicle in a routine traffic stop. It could be very interesting to see how autonomous vehicles affect our lives. Anyway, thank you very much. We'll be happy to answer any questions. And with the sort of the floor is open.
I was addressing most of the questions by typing it in. I wasn't sure if we'll have enough time. But if we want to discuss it, means we can talk about it again, means as well. Means for example, one of the questions I saw was about which the variables that we used, means. And I think I gave the impression that we used only speeds, but that's not really the case. Means we used speeds to manually figure out or also automatically figure out the labeling of the ones and zeros to identify which points, where exactly do we draw the line that the congestion has, or the failure has occurred, and what are the points that could be possible precursors. But our input was it used speeds, it used volumes, it used density as computed from flow divided by speed. I stayed away from occupancy because when you have a mix of different detection systems, means you get different kind of values for occupancy depending on the size of the loop that's drawn, especially in the video detection systems. When you're drawing virtual loops, you might not have a 6 by 6 foot loop that you normally see in an inductive loop case. So the occupancy varies, so it's difficult to tune things to that. So we stuck with density, and it was a mix of those parameters in terms of the differences in the time and space region.
Good, thanks very much for that, Gwyn. I got a question about how we arrived at the thresholds that we employed, and the answer is through a lot of experimentation. Like to think that it was obvious at the beginning just exactly what criteria to use and what thresholds to employ, but in fact it proved not to be that simple. We started out looking at averages. We looked at averages and standard deviations. We looked at fitting the data to parametric distributions like log normal, like gamma, like Burr, and came to the conclusion that certainly can do that, but in terms of a diagnostic tool to identify when these events are occurring, that it wasn't all that helpful. So we went back to looking at the raw data. And as I indicated in the chat box, that it seemed, if you get all the way out to the real fringes of the distribution, the 99th percentile, the first percentile, the noise tends to dominate the signal. And if you get too far in towards the median, then the signal gets lost because you don't see the variation being created by the incidence and the demand because you're too close to the mean, or you're too close to the median. And I don't know that I would argue that the 5th and the 95th are magically the correct values, but it seems that percentiles in that range provide the best information, as opposed to data, the best information out of the data stream that you're obtaining. I hope that helps. Other questions? There are a number of things in the Q&A box.
I see another interesting one. So there's a question about whether I think it will be helpful to bring in data related with lateral movements, lane change, merge, diverge. I don't know if this is for you, Mohammed, but I will I'll answer my part from my side, and you can probably talk about your side. As that those kind of information is typically not available unless you have a connected vehicle deployment. So right now working with the data that we have, at the aggregate level data, we have not taken that into account. But once we have the CV data, we absolutely can and should include that.
Yeah, and I think we discussed this both across the universities and also in FIU, and we tried to do that. I think that again, you have to also consider the accuracy of those and things like that. But I forget what was our conclusion. I know that, and I will possibly go and talk with our team, because I know that we discuss it, and I know we snap those two lanes, the points, and but I don't remember why we didn't use them in the prediction or in the clustering. Maybe they didn't come as significant, but I 100% remember that we snapped them to the lanes and we were planning to use them, but that has been like almost 7-8 months. So I don't know why they didn't appear in the final results. Possibly it was because they didn't come as significant variables.
There was one more question in the question and answer session. It says for non-recurring congestion cases, how do data factors like weather severity, index of incidents, are they being considered, or would they be considered in the unsupervised machine learning methods to help ferret out indicators that these events have occurred? You can read it yourself and just make sure that I read it correctly.
Yeah, I agree. I think those indices are better, and I always thought about this too. They are better indicator if they are based on data and machine learning and other things. They are better indicators than what are incident now defined as severity in the traffic management center. A lot of time they base the severity based on the number of lanes and the duration of the incident and things like that. But if you associate those with impacts, actual impacts, I think that's a better thing.
So Undine, we're coming up to the top of the hour. We're happy to answer more questions. I think we've addressed the ones that are in the chat box and in the Q&A dialogue. Is there something else that you would like us to do?
Oh, I think we're great. I think if any future questions come up, participants, please reach out to one of our speakers today, and we will follow up with a recording of the webinar within the next week.
Great. And we should say that Michael Hunter is here. He was able to join us after we got started, but thank you very much, Michael, for being here. We really appreciate the interactions we've had with you and your group at Georgia Tech.
Thank you. It's been fantastic watching this. You guys did a fantastic job.
Thanks, Michael. So I guess with that, the webinar has been concluded, and we wish you a good day, and you can get in touch with any one of us. Just send us an email. We'll be happy to respond and provide what insights we can.
We did receive one question about speakers' email addresses, and I will include those in the follow-up email with the recording link.
Okay, that'd be great, Undine. Thank you very much.
Okay, thank you everybody for joining us.
Thank you.
Bye.